Hi everybody, welcome to a mini lesson from the chapter 2 material covering pH, acids, and bases. So this is the last little part of chapter 2. Just wanted to touch a little bit on the pH scale, what makes an acid and a base, and some environmental examples with what's going on with our oceans right now, and some neutralization reactions and kind of what that means. So let's get started. All right, so when we talk about what an acid and a base is, a lot of times you're given this example of water, kind of going back and forth between two water molecules and what's called a hydronium ion and what's called a hydroxide ion. So basically, when you have this reversible reaction, right, so we have these arrows going in both directions, it means that these hydrogen atoms are kind of bopping from one water molecule to the next, but they're doing it in equilibrium. So the same amount of water molecules becoming these two things, the hydronium and the hydroxide, are equal to the amount of water molecules that are just our regular H2O. So when we get an acid or a base, it's when these things are not in balance. If you have maybe higher hydroxide or higher hydronium, right? So if you have higher hydronium, you're going to have more of these extra water molecules with these extra hydrogens. And typically we just count the extra hydroniums as high hydrogen, like all by itself, even though hydrogen ions really aren't ever all by themselves. It's just easier to communicate it that way instead of trying to talk about hydroniums. So when we are trying to define an acid, a lot of times textbooks and you'll see references saying acid is a substance that donates a hydrogen ion. So what does that mean? What does it mean to donate a hydrogen ion? It means when you take a substance and you put it into water, right? So you take a substance, you put it into solution, it will break up, and when it breaks up, it will make more of those hydronium ions. It will give up a hydrogen off of its molecular structure to float around in that solution, increasing the concentration of hydrogen ions, okay? So an acid always increases the concentration of hydrogen ions. The reverse of that is a base. So a base is something that when you put it into solution, it will actually tie up, it will accept and bind to hydrogen ions, reducing the concentration of hydrogen ions in the environment. So a base reduces hydrogen ion concentrations. So that's the basic, I don't want to say basic with a base, but that's the general idea. If you can kind of have that be your takeaway, acids increase hydrogen ion concentrations, bases decrease hydrogen ion concentrations, okay? So that's the basic principles of what an acid and a base is. So then take a look at pH. A lot of times the acidity or basicness of something is measured in a unit called the pH. Now the pH scale is a chemical mathematical equation that calculates the concentration of these free-floating hydrogen ions. So in that last slide, when we had the equilibrium between the water and the hydronium and the hydroxide, you had an equal amount of hydrogen ions to hydroxide. So we can look in this little circle here, and if we have 4 hydrogen ions, we're going to have 4 hydroxide ions, and they will go back and forth to equal amounts of water and equal amounts of hydronium and hydroxide. So when you have something that has equal amounts of hydroxide and hydrogen ions, the pH is 7. 7 is neutral. It's right in the middle. You don't have a difference between those two hydrogen ions and hydroxide ion concentrations. So pH 7 is technically the ion concentration is 10 to the negative 7, which is a really small number of hydrogen ions, but that's where that number pH 7 comes from. If you were to start having measuring the concentration of hydrogen ions and things on the acidic side of the scale, the number is going to get lower, right? The pH value will get lower, but what's actually happening is the concentration of hydrogen ions gets higher. So if we take a look at cola, like they're saying this Coke here. So if we look in this picture, look at the difference between the hydrogen ions and the hydroxide ions. We have 1, 2, 3, 4, 5, 6 hydrogen ions compared to 2 hydroxide ions. We have more hydrogen ions. So you have more hydrogen ions is going to give you a smaller pH, right? So if your hydrogen ions go up, that means your pH values are going to go down. So we have less, the value is lower because we have a higher hydrogen ion concentration. I know it's kind of a weird relationship. It's called an inverse or indirect relationship, where you have one thing going up and the result is to go down. So high hydrogen ions will give you a low pH value. So anything less than 7 is what we call an acid. Okay, so this is the acid side of the pH scale. If we take a look at anything that's greater than 7, so here we have Easy Off Oven Cleaner. If we go down and take a look at this circle, we have 1, 2, 3, 4, 5 hydroxides and only 2 hydrogen ions. So in this case, our hydrogen ion concentration is lower, but that's going to give us a higher pH value. So anything greater than 7 is considered a base. So we can see some examples. Seawater is a little bit alkaline, baking soda, ammonia, bleach, oven cleaner, sodium hydroxide is a really powerful base. So in that case, we have a lot fewer hydrogen ions and we have a lot more hydroxide ions. And then here I just have some pictures of some common household acids and bases. You may have these in your home, and that is kind of their characteristic based on their concentration of hydrogen ions or their ability to release hydrogen ions, which is an acid, or absorb hydrogen ions, which is a base. Okay. I wanted to talk a little bit about what's happening in our oceans right now due to an increase in carbon dioxide in the atmosphere. So there is a relationship between carbon dioxide and water in that when you mix CO2 and water, it produces an acid. It produces what's called carbonic acid. And when carbonic acid mixes with water, which it's already in the water being in the ocean, if you'll notice, it produces hydrogen ions. Technically, it is an acid and bicarbonate, but it can also release more hydrogen ions as the bicarbonate. So what we end up with is higher hydrogen ions in solution in the ocean. So when you have higher hydrogen ions, just like in anything, you're going to become more acidic. Now, organisms that have evolved to live and adapted to live in the ocean, which is around a pH of 8-ish is the average pH for the ocean, when we start adding more and more hydrogen ions, we'll notice we're getting into these darker, kind of more acidic levels. And that's going to affect how some organisms can survive. So here, these pictures that I have over here in this little black box, they're showing these production of shells by these little snail organisms. So this first box, this is normal, okay, and for normal. And then as they increased, or I should say increase the hydrogen ion concentration, decreasing the pH of the water that these snail shells were growing in, we can clearly see there's an impact on how well the snail shells can get the carbon out of the water and put them into their shell structure. So the problem that's driving all of this is this increase of carbon dioxide in the atmosphere due to burning fossil fuels and industrial uses and all this stuff that's been happening since the turn of the century in the 1900s with the Industrial Revolution and population increasing and cars and jet, all the kind of stuff that's dumping CO2 in the atmosphere. The ocean is like a big sponge. It's going to take it in because it can, because there's less carbon dioxide in the water than in the air. So things are going to diffuse water. The CO2 will be absorbed into the ocean water, but there's an outcome to that. Because of that relationship with the producing of the carbonic acid, we are acidifying our oceans, and it's affecting the growth of shelled organisms. It's causing bleaching events with our coral reefs. It's really going to be an impact. And what's the problem is it's happening very rapidly. So organisms aren't being able to have time to adapt and take up mutations that might give them benefits to survive these rapid changes in ocean pH. And so we're going to start seeing some organisms go extinct because they just cannot live in environments that are too acidic for their range of life. Okay, so that's my little, I teach an oceanography class in the summer. So if you want a non-major science with lab elective, come and find me this summer. We'll be doing some oceanography. We'll talk about this. But I like to bring that in with this class too, because it's a relevant current event that's happening for you to apply the knowledge that you're learning in these chemistry chapters. Okay, so what do we do with all this acid? We don't, we're constantly breathing in carbon dioxide. You might be saying, Corey, well, how come we're not turning acidic because our bodies are making CO2 all the time? Well, it's true. Our bodies are making CO2 all the time, but we have what are called buffers. So a buffer system allows cells to be able to tie up hydrogen ions if needed or release hydrogen ions if needed to maintain that constant pH. You guys remember homeostasis from our jackrabbit example? So homeostasis, we have to maintain our normal body pH. And our blood in our cells, our average pH is 7.4. So we're a little bit on the alkaline side, just a tad. We're really close to neutral. But if we're to go too far above or too far below that pH range, our cells are really going to have a problem with that. And it could cause death if we get acidosis or alkalosis due to a metabolic disorder or something else that's going on in our bodies. So here's that equation, actually, we just saw with the ocean. Carbon dioxide and water mix to make carbonic acid, and it breaks up into bicarbonate and a hydrogen ion. But what we can see with these arrows is it is reversible. So a buffer is usually something that has the ability to release hydrogen ions as needed, right? So if we are in an alkaline state, we can convert this carbonic acid into bicarbonate and hydrogen ion, and then we can release that hydrogen ion to help us bring us back to normal. If we have too much hydrogen ion, what we can do is we can drive that equation this way, tie up the hydrogen ion and reduce the amount of free-floating hydrogen ion, bringing our pH back to normal. So either direction, depending on what we need, whether we need hydrogen ion or whether we need to get rid of hydrogen ion, buffers allow us to do that. And so our body has a lot of these. When you go into, if you're going to take your anatomy and physiology course, you'll be learning a lot about these buffers to help maintain our body's normal pH. All right, and then lastly, what happens when you mix an acid and a base together? You get a huge explosion? Nope, you might get some bubbles, but usually you will get water and a salt. So, and it's not always just sodium chloride. I use that as an example, but when you mix an acid and a base, you get water and a salt as a byproduct. It's just a generalized chemical reaction. My example that I give us is hydrochloric acid mixing with sodium hydroxide will give us water and sodium chloride as the salt. And what happens is, if you'll notice, the partners just kind of swap places. So if we have sodium is a positively charged ion, and we have hydroxide is a negatively charged ion, the OH negative. Hydrogen is a positively charged ion. Chlorine is a negatively charged ion. So you got to go back to ionic bonds to help you understand where those came from. So when you mix the acid, hydrochloric acid, with your base, sodium hydroxide, the partners just swap, right? So this positively charged hydrogen is going to go and be attracted to the negatively charged OH, and that's going to give us water. The positively charged sodium is going to go and be attracted to the negatively charged chlorine, and that's going to give us our sodium chloride. So we take the ability to accept and donate hydrogen ions away from the acid and base and turn into water, which is neutral, and sodium chloride, a salt, which is also neutral. All right, so that is our neutralization reactions. That's my discussion on acids and bases and pH, and a little bit of an environmental connection to ocean acidification. So that is the end of the mini lessons for chapter 2. So if you have any questions, send me an email, course message, or see me on a Zoom office hour. See you later. Bye.